A very good morning, and my presentation is on high gain multiplier converter for photovoltaic applications. So the paper is authored by myself, P. Balamurugan, and Kaustav Prabhakar, Febindaya, and Mohan Krishna. So the outline of the presentation are the objective, methodology, design, the implementation, results, conclusion, followed by the discussions. The objective of this current work is to design a high gain multiplier converter with reduced switching stress by introducing an voltage multiplier cells into the basic converter, and also to limit the duty ratio of these switches to the extreme levels without going for additional power rated switch. And in addition, we have to extend the switching frequency of the DC-DC converter switches, so which will in turn reduce the values of the inductors and capacitors, and to provide a modular converter in which you can extend the output range what according to the requirement, and to simplify the design of the converter. So for an n stage converter which has one switch, two inductors, two n minus 1 diodes, and two n capacitors forms the resultant high gain multiplier converter. So the basic idea or methodology that is being implemented here is the renewable sources like your solar panel and the fuel cells demands a DC-DC converter since its output is unregulated. So to regulate this DC output voltage, we need a DC-DC voltage converter which is going to provide you an regulated DC voltage. And also, in order to match the DC voltage levels, these DC converters must either to operate in the buck mode or in the boost mode to provide a higher voltage. There is a limitation in the buck mode or boost mode on the duty ratio to limit the voltage levels. If the voltage levels required or the output are quite high, then we need to go for extreme duty ratio, which increases the conduction period of the switch and it reduces the commutation period, which leads to the problem in the DC-DC converter. So in order to overcome this problem, so what we are doing is, in the conventional chip converter, I am going to introduce a small modification, that is an Cockcroft-Walton voltage multiplier stage in between the output of the DC converter and the final output. This is governed by the controller, which is going to monitor the PV panel and the output voltage according to this. In our work, we have limited our application work only with respect to the open loop simulation. So the converter is switched at a constant switching frequency and the fixed duty cycle. So the idea behind this is being explained here, and this is the conventional chip converter where it has two inductors L1 L2 and C1 C2, where L1 and C1 forms the energy pump stage and where L2 and C2 forms the filter stage, and RL is the load, and this the diode and the switch S are going to function alternatively in such a way that the energy is going to be stored into the capacitor L1 and C1 inductor L1 and C1, and again in turn it is being pumped into the inductor L2 and C2. And for this conventional chip converter, the voltage gain is given by D divided by 1 minus D, where D is the duty ratio of the switch S. So now in this case we are going to provide the modification by introducing an Cockcroft-Walton voltage multiplier circuit in the conventional chip converter. So where I have this, I mean this L1C1SD forms the chip converter, and whereas in the output side I am separating this filter stage L2 and C2 to reduce the ripples, and in between this I am using that voltage multiplier cells. So as a result of this, the switching stress is not going to modify, and also the size of the inductor and capacitor are going to remain the same as like your usual design of the converter. So in our work we designed a chip converter with the three stages of the multiplier cells. So in that three stages we have totally six capacitors, C1 down to C6, where C6 forms output capacitor, and five diodes D1 down to D5. Okay, the working of this converter with this multiplier cells can be considered with two modes, with the equivalent circuits of when the switch is closed, when the switch is open. So this circuit shows where the one which the switch is closed, where the inductor charges from the supply voltage and the capacitor C3 discharges and charges C2 through D2. And similarly, the capacitor C3 is charged by the capacitor C4 through D4, and the C5, L2, C6 is going to supply the load. And similarly, when the switch is open, then the whatever the energy stored in the inductor is now being L1 is now transferred to C1, and the energy whatever stored in the previous cycle from C3 it has been transferred to C4, and from C5 it has been transferred to L2 via this D5. Okay, so this is the mode in which the conduction is happening. And using the volt second principle, by equating the current through the inductor and computing the average current through the inductor and average voltage across the inductor, the voltage gain of the designed multiplier chip converter is derived as n minus 1 plus d divided by 1 minus d. So in our work we have designed it for uh, three stages, so that is for n equal to 3 and the duty ratio of 0.5. So for this we got the gain of 5 with the 12 volt input. And these are the design parameters of the designed chip converter, where the input voltage is 24 volt, the output voltage is 120, because the gain is 5 times, and for this 5 times of gain the duty cycle is 0.5. And since we developed the hardware to realize this, we developed a hardware prototype for 50 watts capacity, and which is at 50 kilohertz. So the corresponding to 50 watts and the 120 volt, the output load resistance is calculated as 288 ohms. And following the design of the inductor for continuous conduction, and the input side it is 2 millihenry 5 ampere, and in the output side it is 10 millihenry 5 ampere. The values of capacitors are shown as listed in the table, and we for the hardware we selected a MOSFET of IR of 250 and the diodes MAR 460 with the gate driver IC of TLP 250 for the MOSFET, and the pulses are derived using PIC 3 microcontroller interface. And the whatever the circuit we proposed, initially we tested it through the simulation, and these are the simulation results. And this shows the output voltage of the converter, that is the inverted output voltage of the converter. Actually it is minus 102 volt. Just for the representation I take it the negative voltage of this, and the output current is 0.35 milliampere on an average, which accounts to the power of 50 watts. And these are the voltage across the various capacitors present in the circuit and the voltage multiplier cell. And finally it shows the V0, that is your voltage across the V6 is equal to nearly the 100 volt. This is the hardware prototype of the proposed system, where you have this input inductor and this is the output inductor. In between you have the voltage multiplier cells, and for the testing purpose in the laboratory we used an power supply LD32 002 LD3205 regulated power supply. So from which we are providing a 24 volt input, and this 12 volt input is for your TLP 250, which is going to drive the MOSFET. Okay. and we the volt this is the output voltage measured with the mean voltage of minus 102 volt and the current of 992 milliampere. And next, this is the input current, which is of 2.47 ampere, and it is continuous in nature, and these are the voltages and across the capacitor in the three stages. So in all the stages the average voltages comes to 40 volt, 44 volt, 40 volt. When you sum it up, it comes to 120 volt on an average. So the conclusion, so we a high gain DC-DC multiplier to converter is designed by incorporating your Carcroft-Walton multiplier circuit, and in this case the switching stress is equal to the input voltage plus the voltage across the inductor LDI by dt, and for the same duty ratio the converter gain is quite high. Since the voltage stress is very less, the switching frequency can be extended to more than 50 kilohertz also. And since then we can modify the number of stages in the multiplier cell, it provides a modularity, and it is it can be made it readily available in the market. So you can have a modular based converter in which you can extend the output range, and the converter design is quite simple. That is a basic similar to converter design equations holds good for this circuit also. And for a three stage we have developed and one switch, we require one switch, two inductors, five diodes and six capacitors. And these are the few key references which is being used for this and for the discussion. Thank you.